Today we are covering exponential and logarithmic functions. We're going to refresh your memory as much as we can this time about the properties of exponentials and logarithmic functions, solving, graphing, however much we get through. Okay? So, let's real quick review your laws of exponents. Okay, all of these, I believe, not all of them, the majority of them are in your reference booklet, but let's just review real quick. If you have a to the m times a to the n, what do?
M plus n.
Yes, and the only way this can happen is if your bases are the same, okay? What about a to the m divided by a to the n?
Minus n.
Very good. Again, the bases have to be the same in order for you to do this. When you have a power to a power, you multiply. Good stuff. Anything to the 0 power is?
1.
Not to be confused with something like this. What is this?
It's 7.
It's 7. Because that's going to be 7 times 1, which is just 7. The exponent only applies to that x squared. So you want to be very careful when you begin problems that are being raised to 0 power. What's another way I can write the nth root of a?
A to the 1 over n.
Very good. Okay, the more general form would be the next one. How would you write that?
A with m over n.
Very good. Whatever the numerator of that rational exponent is the power that the base is being raised to in that particular problem, and then the root is the denominator of that rational exponent. And then last but not least is your negative exponent property or law. 1 over a to the n. So also if you have something like this, where you have 1 over a to the negative n, that will become a to the n. And then if you ever had something like this, how can I make it so that it's no longer a fraction? It will be a to the negative n. So don't forget, that property applies across the board with all of these different ones, okay? Exponential functions, okay? Exponential functions, you guys remember what they look like? Draw it on your desk. Draw on your desk. What does an exponential function look like? Draw it on your desk. Yes, think. What things in the real world like model exponential functions?
Student
Population, death,
I said that.
debt, okay, all those things. Which means that if you think about population, isn't it consistently increasing?
That's no bueno.
But if you have people dying off, like there's a disease, it's
like decreasing.
It's decreasing. Y'all remember growth, population growth, and decay? Those were both exponential functions, okay? The general form for an exponential function was y equals a times b to the x, okay? It's called exponential function because your exponent was your variable, was your independent variable. Well, excuse me. What were the domains of these functions? Who remembers?
Negative infinity to infinity.
Exactly. Negative infinity to infinity. All real numbers. What was the range, though? Who remembers?
Should be 0 to 0.
Is 0 included?
No.
0 was not included. There was a horizontal asymptote with these exponential functions. Okay, so we'll get really close to the x-axis, but never cross nor touch. Hence why the range was everything greater than 0. Of course, if the graph is shifted up or down, that does change because the horizontal asymptote shifts up and down. But no matter what was your y-intercept? It was 1. Think about it. If I plug in to that general form, if I plug in 0 for x, well, technically you're gonna get a, but your most basic function was always like 2 to the x or 3 to the x or anything like that. So it's always 1. Of course, depending on what a is, if you want to be a little bit more specific, 0a. Any x-intercepts?
They don't exist.
None. Very good. Now, of course, your transformations apply to exponential functions, just like they did with quadratic functions. Okay, y'all remember all your transformations? Okay. Well, if I give you this,
Oh boy.
okay, what is the most basic parent function first off?
3 to the x.
3 to the x. Very good, because it's whatever your base is, whatever your exponent is being raised to, that was your original parent function. So then that means that 2 did something to the original parent function. What did the 2 do?
It stretched it or vertical.
It was a vertical stretch by 2, which means I would multiply all of my y values by 2. What did this mean? A translation to the right one. Remember, anything inside with the x, or in this case, in the exponent with the x, meant it moved left and right. Remember, everything was the opposite. And what about the 2? It's a vertical translation up 2. Okay? And just to review real quick, if it's written in vector format, that would have been, remember, vector format, that's your x, horizontals, left and right.
Oh, it's so
These were
weird.
your y's, up and down.
I put Y on this.
Vertex.
I did too.
No! Great question. You asked, can the 3 be a 4 or a 5? Yes, it can. So whatever that base value is, that is your parent function.
No, but it's continually decaying if the coefficient is below 1.
Correct. Decay functions, and I'll actually go back. Yes, decay functions occur when your a is in between 0 and 1, and your growth functions were always when a was greater than 1. Yes. Good stuff. So would this be an exponential growth or decay? It would be a growth. Okay. Of course, you got to worry about your reflections and things like that, because those can affect whether it stays growth or becomes decay. All right. Let's look at this one. Okay. What does that negative in the exponent mean?
It means we are making to 1 over 2 to the x.
Oh, what transformation is that?
Reflection over the y-axis.
It's a reflection of the y-axis. So normally, if it was 2 to the x, that means it's exponential growth. But since it is reflected, it's now decaying. What is the domain of this function?
Yeah, negative infinity to infinity.
What about the range?
0 to infinity.
0 to infinity.
Yeah, it's always the lowest value to the highest value.
Always the lowest value to the highest value. Very good. Let's take a look at this one. It says a sample count of bacteria in a culture indicates that the number of bacteria is doubling every hour. Doubling every hour. Given that the estimated count at 1500 was 12,000 bacteria, find the estimated count 3 hours earlier at noon, and write an exponential growth function for the number of bacteria at any hour t. Okay? So first off, we know that the general form for any exponential function is what you see here. Since it's with respect to t, I'm going to use a t instead of an x. Okay? What is b? What's my base?
X.
Your base is 2.
Our base is 2.
Oh.
Because it told us that it's doubling every hour. So when you think about an exponential function, whatever the exponent's applying to is like the scale factor in which is either increasing or decreasing. Okay? That's what causes, like when you go back to the most general form of your exponentials, that's what causes it to be growth or causes it to decay, is that base. Okay? Actually, this was so wrong. I'm glad I went back to this. It shouldn't be A. It should be B.
Oh.
So I'm glad I went back to this page. This should be B and B. That could have been helpful. Okay? So B. If B is greater than 1, it's growth. Less in between 0 and 1, it is decay. So since it's doubling every hour,
It's 2a to the t hour. A to the 2. Yeah, that.
I gotcha. Now it says, given that the estimated count at 1500 hours was 12,000 bacteria, we would use that to help us figure out the value of A. Because technically that's a coordinate. On this graph of this exponential function, at 1500 hours, which is what?
3 hours.
It's like 3 hours, okay? We're at 12,000 bacteria, so that's nothing but a point. Let's see, and we're trying to find the estimated count 3 hours earlier at 12 noon. So we're looking at this axis. The y-axis would represent 12 noon. So what are we going to plug in for t, and what are we going to plug in for y to help us find a?
Y is 12,000. Is 3.
No, y.
0, 3.
12. And then t would be 0.
No, it would be the full 12,000. And t would be 3. So let's figure out what is the value of a. What is the value of a? As I said, you probably might need your calculator. All right, what's the value of a?
1500.
1,500. 1,500. Okay, that's correct. So then the equation that would represent this exponential growth, this model to represent the bacteria, would be y equals 1,500 to the t power.
Yay.
Okay?
Sounds good.
Questions?
Wait, it's already 3:17?